Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to be talking about buffer effectiveness, and we're going to be talking about buffer effectiveness from this video and a few other videos. In this particular video we're going to talk about how the relative amounts of acid and conjugate base will affect the effectiveness of a buffer. So let's get into this. So a buffer is going to be most effective, and what that means is it's going to be most resistant to pH change when the concentrations of the acid and conjugate base are equal to each other. So the relative amounts. So what I'm going to be talking about in this video is the relative amounts, like the amount of acid to its conjugate base, and when this could be applied to the amount of base with the conjugate acid as well. So we're going to be looking at the relative amounts of acid to base and see how that affects the capacity or the effectiveness of the buffer. And so I have two situations set up. So we have solution 1 and we have solution 2. And so we're going to look at how the buffer is affected when based on the relative amounts of acid and base. So here in solution 2 or solution 1, you'll notice that I have equal amounts of the acid and conjugate base. So we'll see how that affects the effectiveness of the buffer. And so here on this solution 2, we have the acid and base. We have the acid is 0.18 moles and the solution and the conjugate base is 0.020 moles. So they're not equal together. So we'll do the calculation and see how these two solutions compare. So let's start with solution 1. Oh, and the other thing you want to note here is that the total number of moles of acid and base are equal to each other over here. So we have 0.1 and 0.1, so that's 0.2 total. And here we have 0.18 and 0.020, and so the total is 0.2 still. So let's start with solution 1. So one of the things you need to do in this case, in both of these cases, we're looking at the effectiveness of the buffer to resist pH change when you add an acid or a base. So in this case, we're adding a base, and we're going to look at how that affects the pH of that buffer. Okay, and so remember, when you're doing this sort of problem, when you're trying to figure out the effect of the effect of an acid or base on the buffer, and you're going to try to figure out what the new pH is, you have to do a table, kind of like an ICF table, where you're not looking at equilibrium, you're looking at how the amount of moles change after the reaction. So in this case, if we're going to add a base, so here I have an equation where we're adding some strong base here, OH minus, and that OH minus is going to react with the acid that's in the buffer. And as we saw in a previous video, that is going to react with the acid. It's going to bring the moles of acid down because you're reacting with the acid, so you're lowering the amount of acid. And that lowering, when you react it, that's going to produce more of the conjugate base. So it's a 1-to-1 ratio. So whatever you lose here, you gain here, right? And so you have to do an ICF-like table where you have the initial amounts, you have the sort of change there, and you also have the final amounts. So it's not an equilibrium where you have E for equilibrium. And so here, instead of ICF, I'm using before I add the acid or base. In this case, we're adding base. So before I add the base, and this is the addition of the base. So here's I'm adding base, and then here's after I added the base. So here's my table, and this is the table you need to do. So because we need to figure out the stoichiometric reaction, right? So what do we have left over after the reaction of the strong base? Because this strong base is going to react completely with the buffer. So we got to do a stoichiometry problem here first before we do any sort of equilibrium problem. So for the equilibrium problem, you could either do an ice table or you could do the Henderson-Hasselbach equation. So we're going to do the Henderson-Hasselbach equation for this one, and then we'll show you what the result is. Okay, so here I have my equation of the reaction of adding base to my buffer. And so initially, before I added anything, before I add the base, we're assuming we have about 0 moles of OH. So there's going to be some OH in there because it's a buffer, right? But it's effectively 0. So I think that's a safe assumption to make. So we're saying it's approximately 0 moles of our OH minus to start. We're starting with 0.1 moles of our HA, so we have that there. And then water, since it's a liquid, it's not involved in the reaction. So we're going to ignore that. We cross that out of our table. And then here we have our conjugate base, and we're starting with 0.10 moles of that. So 0.100 moles of our conjugate base. Now, what are we adding? So at the adding, we're adding 0.010 moles of a strong base. So we're just adding our OH minus, our hydroxide ion here. And we're not adding anything here. So the only thing we're adding is our strong base, our OH minus. So, but the thing to keep in mind here is that the strong base is going to react completely with whatever acid is available. So our HA. So that brings us to our after we add it. So what happens after we add the base? Well, what we have here, we got to remember that this is going to react completely. So this is going to go away. This is going to react completely, and it's going to go back to 0 amount, right? But remember, there's a stoichiometry going on here. So if this reacts with our acid, and it's a 1-to-1. Then that means if we lose this here, if we subtract 0.010 and we get 0 left over, then that means that we're reacting the same amount. So here we could kind of write or understand this as if this is, we're losing here minus 0.10 moles, right? Oops, that should be... So for subtracting, we're going to be losing 0.010 moles there. So that means we're going to be losing the same amount here. So we could be subtracting 0.010 moles here. So that's going to be, this is going to decrease by 0.01 moles. And so this is going to be gained, right? So we're adding the same amount. So it's a 1-to-1 here. So we'd be adding 0.010 moles. So it's kind of like an ICF table, right? So we have our initial, we have our change, and then we have our final amounts here. So that means, so the 0.100 moles goes to 0.090 moles. So we lost 0.0 moles. Because of the strong base that reacted. And then we add the same amount of our conjugate base. So we gain 0.01 moles here. And so here's the new amounts. And notice that we're doing this in moles. So this table doesn't work unless it's in moles. It's a lot easier to do this in moles. And so we can just keep this in moles. So not concentrations. Don't use concentrations for this table. Okay, so now that we have our moles, final moles after the reaction of the added base, now we can do our equilibrium problem. And so we're going to go to our Henderson-Hasselbach equation and work on that. So here you can see these are the amounts of acid and base. we are assuming for this problem that our pKa is 5.00. And so what we're going to do is we're going to say pH is equal to 5.00 plus, and that's going to be the log of base over acid, or conjugate base. So we're going to put in 0.110, and we're going to put in for the acid 0.090. And you'll notice that I'm putting in the moles. I'm not putting in concentrations. It's not molar. I'm not putting in molar. And I can do that because the volumes are going to cancel out. So if I have moles, right? If I have moles of my base over volume, whatever that is, divided by and this is molarity, because molarity is moles divided by volume in liters, right? And I have this in moles, and that's going to be moles over volume in liters. And so since both the acid and the base are in the same solution, same container, same volume, so these are going to cancel out anyway, so it doesn't matter. So I can use moles. I can plug moles in here, and that's just fine. Okay, so what I get here is I'm going to get pH is equal to 5.09. That's what the final result is going to be. So now what I can do is I can find the percent change, right? So percent change is going to, oops, forgot my E. Percent change, that's going to be equal to the pH that I found after the new pH. So that's going to be 5.09 minus the old pH, 5.00, which is what we're getting here. So 5.00. And that's going to be divided by the old pH, 5.00. And of course, multiplied by 100. And we get a percentage that I'm going to calculate right now. Okay, so where's my calculator? All right, so I have 5.09 minus 5.00 equals divided by 5.00 times 100 equals, and I get 1.8% change. So that's going to be 1.8% change. So that's the change in the pH after adding the base to this solution. So let's do the same thing for this solution. So same reaction, same acid. So we're going to be having the same equation here. So, but the only thing that's changed is the relative amounts of acid and base. So here we have a lot more conjugate acid versus our acid versus our conjugate base. So we have less conjugate base and we have more acid. So the relative amounts are not the same. Here again, they're equal, right? 1-to-1. Here, they're not equal. And so here the initial pH we're assuming is 4.05. And so let's go ahead and do our calculation. And so here, again, we're starting off with 0.00 moles. So that's an assumption that we can make because it's a buffer solution. It's kind of like having a weak acid and weak base in solution. And so we assume that the amount of OH minus that we have in our solution is going to be 0, or approximately very close to 0. And we're starting off with 0.18 moles of our acid here, and we're starting off with 0.020 moles of our conjugate base here. So again, this is our initial amounts before I add the base. Now I add the base, and again, we're assuming the same amount. So I'm adding the same amount of base here, as I did here. So 0.010 moles of base. So again, we're not adding anything here. And then this is after I added the base, after the reaction has completed, right? So once again, there's going to be this is a stoichiometric problem that we're working on. We need to figure out how much reacts and what we're ended up with in the end. So here, because this is a strong base, again, this is going to react completely with the acid in our buffer. And so that's going to be subtracted. So we're going to minus 0.010 moles. And that means if we subtract that here, that's going to react completely with this. And so we're subtracting 0.010 moles of VHA that's reacted. And so by reacting that amount, that's going to produce the same amount of acid, or our conjugate base, sorry. So if we lose this amount here, we're going to gain it here. So plus 0.010 moles. And so that's where we get our 0.030. So we add these together, we get 0.030 moles of our conjugate base, and we end up with 0.17 moles of our acid. So now that we have completed our stoichiometric problem, we can plug that in and we can do our equilibrium problem. And again, we're going to use the Henderson-Hasselbach equation. So here the pH is 4.05. So that's going to be, or the, let's see, again, the pKa is going to be 5. And so we're going to calculate the new pH. So that's going to be equal to 5.00 plus the log of, again, we can put the moles in. So we got 0.030. So 0.030 moles over 0.170. I didn't put the 0 in there. And so now we can just calculate the pH. So let's go ahead and calculate that really quickly. So here we have 0.030 divided by 0.170 equals, and then we're going to take the negative log of that. So we're going to take the log and then take the negative. And then we're going to add 5.00 equals. And there we have the pH is equal to 5.75. 5.75. Okay, so now we can do the same percent change. We're going to do the same percent change here. Let's do that here. So percent change is going to be equal to, it's going to be the 5.75 minus 5.00 again, divided by 5.00 multiplied by 100. And our percent change is going to be, so 5.75 minus 5.00 equals, divided by 5.00 equals times 100 equals, and, oh, give me a second. No, sorry, wrong thing. Not 5. My bad. 5 is the pKa. The change, sorry, our initial pH is 4.05. My bad. So 4.5, so it's going to be 5. So 5.75 minus 4.05 divided by 4.05 and if we do that, 5.75 minus 4.05 divided by 4.05 equals, and then we get, what do we get? Okay, oh, I made a mistake. I think I made a mistake in my calculation. Where's my eraser? Okay, so I subtracted here when I should have added. That's where the problem lies. Okay, so let me recalculate this. So that should be, so I did this right. So 0.03 divided by 0.170 equals, and then you take the log of that. Okay, and then you add, so plus 5.00 equals, okay, so 4.25. All right, so I subtracted when I should have added. So 4.25. So that's the pH. That's the problem. Okay, so then that 4.25. So 4.25 minus 4.05. And then now we can get the right answer. So 4.25 minus 4.05, our initial pH, 4.05 equals, and then divided by 4.05. So just like here, equals times 100 equals, and we get a percent change of 4.86. So percent change is equal to 4.86%. And so right away, what you can see here is when the amounts, the relative amounts of your acid and conjugate base are equal, then you get a change of only 1.8% in the pH. So the pH doesn't change as much when you compare it to if the acid and base are not relatively equal. So they're relatively different here. So when you have more acid or base, or more base and acid, the pH, the effectiveness of the buffer is not as good, and you can see that the change here is greater. So when you throw the same amount of base into this buffer, the percent change is larger, so 4.86%. So the pH changes by that much. So that is an example of how the relative amounts of the acid and conjugate base, or base conjugate acid, is crucial to the effectiveness of your buffer. And so the upshot of this is that in order for a buffer to be reasonably effective, the ratio of base to acid should be between 0.1 and 10. And what that means is that the difference in the amount of acid and base should be no greater than, or no different than, a factor of 10. So either the base is 10 times greater than the acid, or the acid is 10 times greater than the base. That's where the 0.1 and 10 come in. So if the concentration of the acid and base differ by a factor greater than 10, then that's definitely not going to be an effective buffer. So you got to be within that range. So I hope this is helpful. Sorry about the mistake that I made here. But if you enjoyed this video, if you learned something from this video, if you got educated by this video, then please, by all means, hit that like button right there. And also subscribe to my channel. Hit that notification bell up there so you can be notified by any other videos I put out. And also put a comment down in the comment section. Let me know what you think if you have any questions. Thanks for joining me. Have a great day.